Good. So, just to recap, a bit on what we were talking about last week. So we talked about reinforcement learning versus supervised learning, different models of optimality, the need for exploration versus exploitation, and then we were looking at two different kinds of reinforcement learning. So one of them is value function learning, the other is policy learning, and within value function learning we talked about Q learning and TD learning, and within policy learning we just started to talk about this. So within policy learning we're going to have evolution strategies and also policy gradients, and finally there's this actor-critic scenario which actually combines policy learning with value function learning. Okay, so this was the formulation of reinforcement learning frameworks. We have a set S of states and a set of actions, and we have a transition function and a reward function which can be probabilistic, and the agent has a policy which can also be probabilistic. These were the different models of optimality. We talked about how infinite discounted reward is usually the preferred model. And we kind of had a look at a couple of these simple environments, so what the optimal policy is, and so on. And that was the Q learning and the TD learning, and then we went through backgammon as an example of an application of TD learning. Okay, so now we move on to policy learning. Now, policy learning, instead of learning a value function, we'd learn directly a policy. So the value function learning, we either learn the value of a state or we learn the Q value of a state and action combination. And if we've learnt the value, and the training is done to try to minimize the distance between this our estimate of the cost function and the true cost function. And then once we have that cost function, if it's Q learning and we're in a particular state, we just pick the action which maximizes the Q value. We pick the A which maximizes Q of S comma A if S is the state we're currently in. So the Q learning works whether or not we know the transition function. We don't have to know the world model if we're using Q learning. All we have to know is the Q function, and then we get the policy. With TD learning, we only have the value of the state. So if we have the value of the state, we also need to know the world model, because if we're in a particular state and we want to choose the right action, we have to know which state an action is going to take us into. And so for all the actions available for us, we figure out which state that action would take us to. We look at the value of that state, and then we pick the action that maximizes that value. That's what we were doing with the TD gammon. Okay, so that's value function. Now the policy learning doesn't necessarily involve a value function at all. We simply have a policy. We'd simply look at this policy that takes directly states to actions. So we might have a neural network where we put the state in and the action comes out, and we have certain parameters in that policy. So again, we usually think about neural networks. So the theta here represents the weights in the neural network. So we sometimes use W for that. Here we're using W for other things. So it's traditional to use theta for this. So theta, the weights in the network are theta 1, theta 2, etc., up to theta n if there's n weights. And so the idea is to find values for those weights theta that will give us the optimal policy. So in other words, the policy that will maximize the reward. Okay, so the fitness of a policy is the expectation of the reward. Well, there's a couple of ways to write this. So let's say that the start state is S0. S0 is the initial state in the game. Then V pi theta of S0 is the value that the reward, the average of the reward that we expect to get starting from state S0 if we follow policy pi theta. So that's the thing we want to maximize. And this is sometimes written like this: the expectation, if we follow policy pi theta, of the total reward. Now, I'm going to first of all talk about evolutionary learning, and then afterwards policy gradients. So this evolutionary strategies is actually kind of again, it's these. We look at old examples from the 90s, and then we look at the modern, how these have been applied recently with deep learning and very deep networks. So this is a very kind of simple algorithm in a way that we used in the 90s, actually on backgammon and also on some simulated tasks like robot hockey. And the way this algorithm works as follows. So we want to, theta is the weights in the network. So we have a network which defines the policy for a particular game. And let's think it could be a single player game or a two-player game. So these weights, we start with some initial value for these weights. We could start just with all weights equal to 0. Now, at any given point in time, we have a certain value for these weights, and we call this the champ because this is the best player that we know of at the current point in time. So we call that the current champion. And then what we do is we randomly we find we make a small change to these weights. We start with the champion weights, and then we add a small amount of random noise to each weight selected from a Gaussian distribution, and that gives us a new set of weights which we call the mutant. And then we evaluate the champ and the mutant to try to guess which one is better. We want to see whether the mutant is better than the champ, so we evaluate the champ and the mutant on the same tasks. And calculate the score. And then what happens? Well, if the champ in this original algorithm, if the champ does better than the mutant, then we just throw that mutant away and generate a new mutant. But what happens if the mutant is better than the champ? Well, we could just throw away the champ and take the mutant. That would be called hill climbing. But we introduce this slight variant where we say, okay, I'm not going to just replace the champ with the mutant. I'm going to replace the champ with a weighted average between the champ and the mutant. Now, why is this? Well, let's suppose we're learning backgammon, for example, or some other game. We can't play every possible. We can only do a limited amount of testing between the champ and the mutant, right? So let's say the champ and the mutant play, 4 games against each other with the same dice rolls. Well, and then based on games with that particular set of dice rolls, the mutant has done better than the champ. But we don't know for sure whether the mutant would beat the champion if there was a different sequence of dice rolls, right? So by using this alpha, and a typical value of alpha would be about 0.1 or 0.2. So if it's 0.1, we're taking 90% of the current champ and only adding 10% of the mutant. So this is saying, well, the champ has emerged from a long series of previous games, so we have a fairly high confidence that the champ is a good player, but the mutant has beaten the champ only in these 4 games, so we only we have less confidence that we think that the mutant's better than the champ, but we're not really quite sure, so we take account of that by just adding a small component in the direction of the mutant. So this, these weights can be continuously adjusted, and so in Euclidean space, we're kind of drawing a line from the champion to the mutant and just going some fraction of the way along that line. And this is another word for this is this is sometimes called evolutionary strategies. This kind of approach. Now, so I'll just show you one example. Now, those of you who took my AI course will have seen this before, but it's just a very sort of simple and tangible example of this kind of thing. So we have this kind of simulated hockey task. So the aim here is for the player to hit the puck into the enemy goal and avoid it going into your own goal. And so what we do here, in this experiment, it's a 2-player game, but when we're training, we don't have the other player. We actually just have one player and the puck, and when we do an episode, the player starts at a random location, and the puck starts at a random location, and then the player has 30 simulated seconds, and if it manages to get the puck into the enemy goal within those 30 seconds, then it scores a point. If the puck goes into its own goal, then it gets -1 point. And if the time elapses, it gets 0 points. So we just implemented this in Java. It's a rectangular rink it's got rounded corners, so that prevents the puck from kind of getting stuck in the corner there. The playing surface is close to frictionless, so you can adjust the physical parameters. If you make the friction larger, then it sort of simulates a ball rolling along. If you make the friction small, it's more like an air hockey kind of game where it's a puck sliding along on a cushion of air. So in this case, we make it more like a hockey thing. Collisions are handled there's a couple of different ways to handle collisions. We use the spring method, which is useful when it's often the case that 3 objects are in collision with each other. And the puck, we decided that the puck wouldn't spin. So when you look at Pong, we're going to look at some videos later of this game from the 1970s called Pong. In Pong, they tried to implement the idea of the ball. So when you play table tennis, if you hit the ball, if you sort of slice the ball, then you can put spin on it, and then when it bounces, it'll bounce in a slightly sort of skewed way, and people often use this as part of their strategy. If you look at Pong, they tried to implement this spinning of the ball, but it's implemented in a very crude way and is very physically unrealistic. So when you play Pong, it's a bit frustrating in a way sometimes when you play Pong, because the ball just bounces at a funny angle that you can't even predict often. So we just didn't have the ball spinning. Now the way this is implemented, we imagine that the puck has 2 sort of skates and a skate on each end of its body with which it can push on the table in 2 different directions, and the sensors the details of this aren't too important, but the sensors here are like what we call Breitenberg style sensors. So we have 6 sensors pointing in different directions, and each sensor is a bit like a sort of sonar thing, that it has a receptive field of 90 degrees, and so if the puck is outside of that 90-degree range or the distance is too far away, then this sensor returns a value of 0. if the puck is within the angle specified, then it returns a value between 0 and 1 depending on how close the puck is. So if the puck's very close, you get a value close to 1, and if it's far away, you get a value close to 0. So there are sort of 6 inputs here to detect the puck, and we also have 6 similar inputs to detect your own goal, and 6 inputs to detect the enemy goal. So it can detect the puck, it can detect your own goal and the enemy goal. Interestingly, it can't detect the opponent. The opponent is actually invisible, but it can detect other things if they're in range. So we have 6 sensors for each of these stimuli, so that's 18 sensors. We have 3 additional inputs that specify the current velocity of the vehicle. So the velocity meaning the instantaneous, well, it's like basically it's the difference between your current position and what your position was at the previous time step. So there's 21 inputs in total, and in this experiment, again, this is back to the old days of these very shallow networks. We have 21 inputs, and we basically just have a linear function. So it's a one-layer neural network, effectively, and there isn't, the only transfer function is like a cutoff. So the output is the force, and you're only allowed, there's a certain maximum force that you're allowed to apply. So if the value exceeds that maximum force, the force gets truncated, but the direction is preserved. Okay, so this sets up the genome for this evolutionary algorithm. So these parameters theta, there's only 88 parameters in this network, and the Gaussian noise that we add has a standard deviation of 0.05, and again, each game begins with a random game initial condition. So random position for the puck, random position for the player, and then the score is just based on whether you score a goal or not, or whether you score an own goal. And when we measure the champ and the mutant, they both start from the same game initial condition. So we start with the puck in a certain place and the player in a certain place, and the champ network is the controller, and it plays for 30 seconds, and we see whether it scores a goal or not, and then we try the mutant from exactly the same game initial condition. So we try to, by having the same game initial condition, we try to kind of reduce the variance in the fitness evaluation as much as possible. And so what happens here? Well, for the first 1,000 games or so, it almost never scores a point. But then at some stage, randomly, just by chance, it happens to get some lucky initial condition where the ball is right in front of the goal and the player is right behind the ball, and all it has to do is sort of move forward, and it can hit the ball into the goal. So the learning kind of starts off from there, and then it gradually is able to score goals from further and further away. And I've got some videos of this. So this is after 50,000 games of evolution. So it's a bit sort of awkward. This is 100,000. It does get the ball in, but it's clumsy. Here it's become more. This goes so fast. Let's watch this again. So what you're going to see, we see, first of all, we see 3 different stages of evolution from the same game initial condition. So at 150,000 games, it comes through and really smoothly hits the ball into the goal. But then we tried, it's interesting to see if the ball starts along the edge, it can sort of nudge it off the edge. And then here, notice what happens here. It accidentally hits the ball towards its own goal, and the evolution allows it to learn to come in and save it from going into its own goal. So that behavior becomes very important when you put two of them in the ring, in the rink together. And I might also point out, it's kind of interesting, we try to have the most pure possible fitness function. So I don't have videos of this, but we tried some experiments where, you see how it swoops in and saves the goal there. We tried some experiments where, to get the evolution started, we would offer some sort of partial credit. So if the player hit the ball, player hit the ball towards the goal, then we would give it some score, but not a whole point, but maybe 0.4 or something. And then if it didn't hit the ball, but it moved closer to the ball, then we would give it some smaller penalty, like 0.1. And what we found is that actually disrupted the evolution. So it started out to learn fix earlier, but it would sort of it would hit the ball it would hit the ball, and the ball would be right near the goal, and then it would just leave it there. Because if you anthropomorphize this, it thinks, well, I'm going to get the credit because I moved it really close to the goal, but if I go and hit it again, there's a risk I might hit it away from the goal, so it's safer to just leave it where it is. Or sometimes it would just circle around the ball and not hit it because it knows it's going to get the credit for being close to the ball. So that's a sort of general lesson with this, any kind of machine learning, but especially evolution, that sometimes when you put in these partial credit and stuff, it has effects that are counterproductive. And finally, this is what happens when we put two players together. So each of these is evolved separately on its own, but they're both one's shooting for the top goal and one's shooting for the bottom goal. So you get quite an interesting battle happening here. Very good. And also in terms of robustness, there we go. The fact that we evolved from different game initial conditions is also important. If you always evolved from the same initial condition, you may learn a strategy which is very, very brittle. Okay, now we also applied this to backgammon. Now, in the case of backgammon, what do we mean by starting with the same game initial conditions? Well, we have the champ and we have the mutant. So the champ plays, so in one game the games are played in pairs, and in one game the champ plays first, and in the other game the mutant plays first, but in both games you have exactly the same sequence of dice rolls. So having the same sequence of dice rolls tries again, it's this idea of trying to reduce the variance in the evaluation. Now, of course, it's not perfect because a dice roll that's good in one situation, once the games diverge, a dice roll that's good in one situation might actually be bad in another. But there are some dice rolls that are almost always good or generally good. Rolling a double is usually good, for example. And when we first did this work, we put our player up on the internet, and this is in the mid 1990s, and people could go in and play against our player, and people were somehow convinced that we were rigging the dice rolls to favour our player. People would get beaten by the player, and they'd send us an angry email, "Oh, I'm sure that you're rigging the dice rolls." But in fact we weren't, we were just generating them randomly. And what we found is that this thing did learn to play backgammon. It wasn't quite as good as TD gammon. So TD gammon, which was trained by gradient descent using TD learning, played better than this method, a little bit better. Possibly because the method's a bit more precise in adjusting the weights, or there's certain weights that rarely get used, whose values can drift with evolution. Okay, so that's the evolution is one form of policy learning. By the way, I should mention there is something a bit, there's a bit of a subtlety here because at first sight it may look as if this is the same as policy learning because it's using the same network structure as TD-gammon, so the network is actually being used to estimate a value. But the key thing here is that it's not that the value is, it's the learning is done to select the policy which maximizes the reward. It's not being trained to adjust the value. So that's why it's a form of policy learning. Okay, and then the other method of policy learning is called policy grading. So this is where we actually do use backpropagation, but we use backpropagation on the policy network. So you start to think about this. So let's think about this in relation to Pong, because Pong is one of the first places where this was applied. Let me just let's just try to remind ourselves about what Pong looks like. Sorry, I made a list of videos of some of these. Yeah, so Pong. So the action here, this is simpler to some of these other Atari games because we've really only got two actions. We either move the paddle up or we move it down. And so this is a video of an agent learning to play Pong. And so here, well, let's first of all talk about the input to this network. So with the hockey game, we only had 21 inputs, but here the input is actually the image itself. The input to this network is actually an image of the game, and the structure of the network is like a convolutional neural network. So this was some of the early work coming out of DeepMind on these Q-learning for these games. So you have a convolutional network similar to the ones that were used for ImageNet. So you have multiple layers, you have convolutional layers and then pooling layers and so on. And at the top, you have two outputs. Then you have fully connected layers, and at the end you have two outputs. So one output tells you to move the paddle up, and the other one tells you to move the paddle down. And then the question is, okay, you've played the game. Let's say you play a game and you record. You keep an image of the game state at regular intervals, maybe at intervals of 1/20th of a second, and you have an action that's been selected by the network at each time step. How do you train that network? So this is the idea. You say, all right, at the end, in this situation, you look at the total reward at the end. So again, this is sort of a simpler situation, because with Pong, we assume that there's just only a reward at the end. Like the same as backgammon, you don't get any reward along the way. It's just at the end of the point, you either get +1 or -1. If you win the point, you get +1. If you lose it, you get -1. So we have this R total, which is ± 1. And then the philosophy is, okay, let's say that I win the point. So I've got a reward of +1. And these are the actions I took. Now, I don't know which actions actually contributed more to the reward. I don't know whether I don't know whether this action was important or this action or this action. So what I do is I just treat them all equally. And I say, well, what I want to do is, because I won that point, I want to increase the likelihood of, for every action that I did during that game, I want to increase the likelihood of choosing that action again in the same situation. And if you lose the point, then you say, okay, for every action that I took, I want to decrease the probability of taking that action. So there's no sort of clever credit assignment here. We're just treating all the actions equally. So what do we want to increase or decrease? Well, remember, because the policy pi determined by the theta is written like this, this is the probability of choosing a certain action in a certain state according to that policy. And so this value here is the product of the probabilities of choosing each individual action. In other words, that's the probability of choosing that entire sequence of actions. And if we take the log of this, it turns the product into a sum, and we get the sum of the logs of all these probabilities. So this is what this is what they use for their gradient descent. They try to either increase or decrease this depending on whether the reward is +1 or -1. And this is called policy gradients. Yeah, so this is a very, very sort of simple, in a way, again, a sort of simple, elegant algorithm, but it does happen to do a good job for certain domains like Pong, right? So we say, remember again, R total, now, so with Pong, the R total is either +1 or -1, so this kind of works out nicely. And this, remember, this can be calculated using, this probability can be calculated using softmax. We're familiar with that already. Now, there are some situations, let's suppose I have a game like Pong, but instead of getting +1 and -1, if you win, you get 5, and if you lose, you get 4. Well, then the learning, eventually it can learn, but this kind of stuffs it up a bit, because if you lose, you're still you're still increasing the probabilities of those actions, but you're not increasing them as much. The learning is more efficient if you're sometimes increasing and sometimes decreasing. So what we often do is subtract off a certain baseline, and then instead of multiplying by this R total, we multiply by R total minus the baseline. So if it was 4 and 5, the baseline might be 4.5. So then we're sometimes having a positive number and sometimes a negative number. Yeah?
I think I remember reading that with Pong, to get a better sense of the direction of the ball, they took like the difference between 2 frames in the game. I think I remember reading that somewhere.
Yes, that's true. So Pong, yeah, okay. Sometimes I think I'm not. Yeah, that's a good point. So remember what I said with the hockey player. We took the velocity. So this actually, in order to get the same effect with the Pong, sometimes they take either two consecutive frames or 2 frames as a little bit of a time difference apart, and feed them both into the network. That's right. Yeah, good point. So that actually kind of tells you, and Pong is sort of well suited to this, because Pong if you can imagine, if you took 2 consecutive frames, the only thing that would change really is the ball and perhaps the players. Yeah, so Pong Pong is easy in a sense, because the things that change from one frame to the next are in some sense the only things that are important. Yeah, so that's partly why this is easier to learn. Whereas if you take a game like, for example, Mario, there's things that aren't moving, but are still important. Yeah, well, that's true with a lot of games. Yeah, good point. So this subtracting off this baseline gives us what's called the reinforce algorithm. It's funny, the reinforce is a sort of funny name. It's a bit of a generic name, but this was actually one of the early reinforcement learning algorithms from 1992, apparently. So it's exactly what I described, but you've got this, you're subtracting off this baseline, and that's the policy gradients, okay? Now, what if we want to learn a different game, like, for example, Pac-Man? Yeah, so let's, again, let's remind ourselves what these things look like. So let's just have a bit of a look at something that's learned to play Pac-Man. I think this is using deep Q learning, but all these algorithms are sort of similar in a way. So here, this is the early stages of learning. It dies pretty quickly. This is a little bit further along. It's doing pretty well. But eventually it dies, and then at some point it gets to the point where it's winning 95% of the time. So now it's actually quite good. Now, so one thing you notice with Pac-Man, it's not, it's different from Pong. In Pong, you only get a point when you only get reward at the end of a point, but here you're getting reward continuously along the way. Every time you eat one of the little dots, you get a little reward, and in some versions there are fruits and stuff as well, and you get a reward for that, and if you eat a ghost, you get a reward for eating the ghost. So in this kind of game, you're getting rewards continuously rather than just like one reward at the end. But so these policy gradients can be extended to that situation, and the way it works is this. Okay, how do we think about this? So every policy, so again, every policy determines a distribution on states. So you sort of look, the probability of a state S, the way you think about it is, let's say imagine that I have a particular fixed policy and I play lots and lots of games. So I start in the initial state, I play the game with that policy, and then I go back and I start in the initial state again, and I play the game again with that policy, and let's assume there's some randomness in the game so that it doesn't follow exactly the same course each time. And I imagine I play the game over and over again, and then I figure out how much time I spend in each particular state. So there's theoretically some probability distribution on states determined by that policy, right? So if it plays Pac-Man well, then states where a lot of the dots have been eaten will have a high probability, right? But if it's a very bad policy, they'll have a low probability. So theoretically, this probability distribution exists. In practice, of course, we can't sort of measure it for a particular policy, but this is just the theory in the background. And then what we want to maximize, or the fitness, if you like, of the policy is the sum over all states of the probability of being in that state times the Q value, the sum over all states of the probability of being in that state multiplied by the sum over all action, multiplied by the value, multiplied by the sum over all actions of the probability of doing that action in that state, following this policy, and then multiplied by the Q value of that state and action. So remember the definition of the Q value. The Q value is the cumulative reward that you get if you first do that action and then afterwards follow the policy, right? So this expression here is the cumulative reward you're likely to get from state S, and we multiply that by the probability of being in state S. And this, if we add or aggregate all of this together, this is actually the fitness of that policy. Yeah. And now sometimes we have a discount factor. Notice this gamma to the t. So we imagine that the game is in certain time steps. So if it's a sort of continuous game like Pac-Man, nevertheless we divide it up into individual time steps of like I said, a 20th of a second or something like that. Sometimes we have a discount factor here. We use gamma instead of lambda, but this serves the same role. This is the same gamma that we used in our infinite discounted reward. So if we want, we can discount states further into the future when we calculate this probability. So this is sort of a weighted, so you look at there's a probability distribution at time 1 and at time 2 and at time 3 and so on. If we want, we can weight the states further into the game less heavily. But it's not always necessary to do that. So in certain games that we call episodic games, we can get away with having gamma equals 1. So what do we mean by episodic? Well, if you think about Pac-Man, there's a certain time limit on any particular level of Pac-Man. You can't, it's unlikely that you would play for 3 hours on one level, because eventually either you eat all the ghosts or one of the ghosts is going to eat you, kind of thing. Or I think if you eat all the fruit, if you eat all the pucks, then you move on to the next level. So because there's a sort of natural sunset on the level, we don't have to discount the future. We can just take gamma equals 1. If there was a game that somehow was allowed to go on for hours and hours and hours, theoretically we would have to discount the future, because otherwise the probability distribution somehow becomes unwieldy. Okay. Now, right, so we were talking about policy gradients. Now, if there's something, again, we've got to try to put ourselves into the mindset of the people who devised these algorithms. This is the thing we want to maximize, but it might be quite difficult to directly alter this and this. This distribution here and this distribution here might be hard to affect them, but this is the thing that we can sort of affect most directly. So one approach is just to ignore this and this, or we don't attempt to adjust the row or the queue. We simply try to adjust, we just accept whatever row and queue the current policy has and try to maximize try to maximize this part, try to adjust this part to maximize it. And if we're lucky, maximizing this might eventually give us a very good policy overall. It sort of depends on the domain. So if we're talking about policy gradients, that's actually what happens. We only learn this, we don't learn these two things. But in a minute I'll talk about the actor-critic algorithm in which we do adjust both of these. Okay. So now we get to the log trick. Now this is an important little trick that's in a lot of these algorithms, this log trick comes up. So let's first look at it mathematically, and then let's talk about what it really means intuitively. So we're trying to maximize the sum over all actions of the Q function times the probability, and so this is a gradient. So remember, we're doing gradient descent. So this grads, I don't know, some of you may not have seen this symbol here, but that nabla symbol means we take d by d theta. For each I, we take d by d theta I, and that gives us a vector, and then we move the weights in the direction of that vector. So remember, we had this equation that said theta I equals theta I plus eta times d something by d theta I. This just kind of encapsulates that in one equation. We calculate the gradient for each, we calculate the derivative for each weight, and we put them all into a vector, and then we add that vector. Now, look at this side of the equation. So this is d by d. Well, let's work backwards. Let's suppose we took d by d theta I of log of pi theta I. Now this is, again, we've got to sort of go back to our high school math. If you take d by dx of log of f of x, that's equal to 1 d by the derivative of log x is 1 over x. So the derivative of log of f of x is 1 over f of x times the derivative of f of x. That's what we're using here. So the derivative of log of pi theta is equal to the derivative of pi theta divided by pi theta. So this looks sophisticated, but this is just the chain rule from high school. This is just the fact that the derivative of f of x is 1 over f of x times the derivative of log fx is 1 over fx times the derivative of fx, right? So that's all we've used to get from here to here, high school math, right? And then this cancels that, and we end up with this. So this is the thing we originally wanted to compute, and it turns out that it's can be written in this form. And so when we do our policy gradients, when we do the gradient of the fitness, that was the gradient of the fitness, but then we can replace this grad theta of pi theta by this. So this is actually, we replace this with this, but then we have to multiply by pi theta to cancel out that pi theta, right? So this becomes the expectation of the policy of Q times the gradient of log of pi theta. So there's two, okay, so that's the mathematics of this. Now what about what's the intuition behind this? Well, maybe there's probably two ways to look at this. So one way to look at it is just to say that we often take the log of something. So we've seen this so many times. When we did softmax, we started with a probability, we computed the log of that probability, and then we did the gradient on the log of that probability, right? The same thing was true when we did the sum squared error really came from the probability being a Gaussian, and the log of that Gaussian was a squared function. So that's one way of viewing it, is just say, well, we've taken the log of the probability many times before, so we might as well do it here as well. But the other way of looking at it is to say, well, when we're playing, let me see how this works. When we're playing the game, how should I put this? When we're playing the game, I'm not quite sure how this fits into the equation, but the only way, when we're playing the game, and it's only from what we actually observe while we're playing that we adjust our policy. And the problem is that we have a certain policy we're following, and certain states are going to be more common in that policy. So there's kind of a bias here towards the states that that are determined by your current policy. So what this effectively does is it says, okay, well, if I get into a state that's actually rare, I'm going to boost that state up to some extent. So, let's say I have a state that let's say I get into a state whose probability is 1 over 10. I get into a state whose probability is 0.1. That's a state that I see all the time. So I see that state all the time, so I'm updating my policy for that state all the time. But then I sort of do something unusual, and I get into a state that is only occurs with probability, say, 0.001. So it's 100 times rarer than that other state. So effectively, what this does is it boosts up the learning for that rare state to some extent. So it doesn't multiply the rare state by 100. If the rare state occurs 100 times less often than the common state, it doesn't multiply the learning rate by 100, but it does multiply the learning rate by some factor based on the log of the probability. So it's when you see a rare state, you increase the learning rate for that rare state to compensate for the fact that it's rare. To compensate for the fact that it's rare for your current policy. It might actually be an important state in the optimal policy. Okay, any questions about this? All right, and then finally, as I mentioned, the actor critic. So we've got a product here, we've got the Q function, and then we've got the policy. So with policy gradients, we don't bother trying to adjust the Q function directly, we just adjust the policy. But there's an alternative approach that says, okay, there's two things here. I've got the Q function and I've got the policy, and I'm going to try to learn both of them at the same time. So this is actually the problem. What people realized is if I try to adjust the Q function and the policy using the same parameters, it kind of becomes a bit of a mess. But I can treat this Q function as just having different parameters. This Q is a function of a state and an action. So if I look at it, if I try to see it in this form, what's the Q function determined by that policy? It's really hard to say what Q function is actually determined by that policy. But But I say, okay, well, this is just I want to try to estimate the Q function of the optimal policy by having a different set of parameters W. So here, again, you would have another neural network. So let's think about this. So the policy pi theta, the input is a state and the output is an action. The neural network for the Q function, the input is a state and an action, and the output is a number. Right? So the structure of the neural network is different, and the weight, that's why we use a different letter for the weight. So the weights of this Q function we call W, and the weights of this policy network we call theta. And so the idea is I'm going to try to maximize, I'm trying to learn both of them at the same time. So theta is trying to learn the optimal policy, and W is trying to learn the optimal Q function, and they're learning at the same time. And you hope that they're going to kind of, each one is going to sort of benefit from the other somehow, and that they'll converge to something similar, or that you'll hope that the Q function will converge to something corresponding to a similar policy. And it's called actor critic because if you could think about this a different way, well, the policy, so you remember you've got the policy network theta and then you've got the Q network W. The theta network is the one that's actually choosing the actions, so that's why we call it the actor. The W network is not choosing the actions, it's just trying to evaluate the actions of the other network, so that's why we call it the critic. So you've got one network that's actually choosing the actions, and you've got another network that isn't doing anything in the environment but is just watching what the actor does and trying to estimate the Q function for what it observes of that actor. So that's why it's called an actor critic approach, because the pi theta is the actor and the QW is the critic. And this is so this is how we get the actor critic algorithm. So again, yeah, like all these things are all these algorithms share common elements. So what happens here? All right, we so for each trial, we start in the S0 is the starting state of the game. We select the first action from this probability distribution, and then for each time step, we measure the reward. When I say we sample the reward, we just measure what reward we actually get at that point in time, and then we see what state we go into, and then we choose our action randomly based on the policy, and then these are the learning part of the equation. So what's going on here? Well, this is exactly Q learning. Right? This is the equation for Q learning. dE by dQ is the reward plus gamma times the Q function of the next action minus the Q function of this action. If you go back, this is exactly the Q learning from the earlier slides from last week. Theta, this is the policy gradient equation. It's the, the learning rate multiplied by this Q function multiplied by the grad of the log using the log trick. And the weights are adjusted based on this Q learning, right? So it's Q learning so it's Q learning with the neural network in there. So this Q learning tells us the training signal. The the difference between the target and the output and the target, and then of course we need to use backpropagation to backpropagate the weights through the network, right? So this looks like a complicated slide, but if you just look at it piece by piece, each individual component makes sense. Okay. Any questions about this? Good. Okay, so now we move on. So now I'll start. So that's all the kind of basics, and now we move on to the modern applications. Yep. The actor critic. I'll show you some videos as we go along. Yeah. Okay, so this is a bit of a timeline of reinforcement learning, and so 1961 there was this Menace tic-tac-toe player by Donald Mickey, which I'll talk about in a minute. Reinforcement learning kind of, so there was a bit of work done in the 60s and early 70s. Mainly Donald Mickey working in Britain. Then there was a sort of AI winter, and there was not much research kind of waned, but it's kind of came back into favor in the late 1980s with the work of Rich Sutton. So this TD learning that we talked about, and TD Gammon. And then if you move to the very modern stuff, this deep learning for Atari games kind of started in a big way in 2015. 2016, we had this A3C network. And then I talked about evolution. So the evolution stuff has been applied in modern times as well. So by OpenAI, this is kind of the timeline. And then now all of these methods are kind of very general and don't rely on having the world model. If you know the world model, if you're playing a game like chess or checkers or Go, and you know the world model, then you have the opportunity to do tree search and look several moves ahead. And there are special algorithms that actually combine learning with tree search. So we're not going to talk about them in this course too much. But here's a bit of a timeline of that as well. So the first instance of this actually is Samuel's checkers program back in 1959. There was like TD Leaf and Tree Strap, and then most recently AlphaGo and AlphaZero as well, which has been applied also to chess. Now, this is... I sort of love this because it's a very, very simple or very tangible kind of algorithm for reinforcement learning. This was invented by Donald Mickey, and Donald Mickey was a very interesting character. He actually worked at Bletchley Park with Alan Turing on the code breaking during World War II, and towards the end of his life, he actually was a frequent visitor to this computing department here at UNSW. He was spending 6 months of each year in this department and the other 6 months at Edinburgh. So I knew him actually quite well. But this is work he did way back in 1961. So he was looking at how to play this game of tic-tac-toe, and his algorithm consisted not of an electronic computer, but actually all of these matchboxes. A lot of matchboxes. There's a picture of him with his hand handling one of the boxes. And just briefly, the way this worked was, this is this game that children play where you take turns playing either a cross or a zero in the squares. And what he did is he created a map for every possible position, he created a matchbox, and then for every possible move from that position, he had a bead in the matchbox. So there's 9 possible moves, and he had 9 different kinds of bead, and in each matchbox with the set of beads corresponding to the squares that were still blank in that position. And the way the thing learned was as follows. You play against it, let's say a human plays against it, and every time it's the turn for the machine to move, you find the matchbox corresponding to the current state, you shake the box, you open it up, you pull out one of the beads at random, and that's the move that you play. Okay. Now then at the end of the game, if you lose the game, then the assumption is that the last move that you played must have been an error. So if you lose the game, if the system loses the game, you go back to the last matchbox, you find the bead corresponding to the move that it played, and you take that bead away and throw it away. And so the next time it gets to that situation, it won't be allowed to do that move again. And sometimes you need to backtrack. So if you go back to the last box and there's only 1 bead left, you're not allowed to take away the last bead. So you have to go back further up the game to the second last move that it played and take away that bead. So you keep tracking back until you find the last move it made where it had an alternative, and you throw away the corresponding bead. So it's a very kind of direct negative reinforcement that every time you make a mistake, you take away the opportunity to make that mistake again. And sometimes there's slight enhancements to this. If you make a good move, sometimes you put an extra bead in corresponding to that move. There's a couple of sort of different variations. This is the basic idea. And yeah, I read about this when I was 10 years old in the 5th grade. I read about this in a book by Martin Gardner, and a classmate of mine and I followed his instructions to make these little boxes. So he realized that the number of boxes in tic-tac-toe was too many, so he based it instead on an even simpler game, which is called hexapawn. And this was really the start of reinforcement learning. So he adapted this. He adapted this into a general reinforcement learning algorithm, which is called boxes, and he demonstrated how that algorithm can be used for other tasks, such as the pole balancing. I think I was talking last week about pole balancing. He actually showed how this algorithm could be used to learn to balance a pole. Now, interest in AI sort of faded in the 1970s. A lot of it was because of the Light Hill report and various other things. There's a long history to this, but there was what was called the AI winter, and machine learning in particular was out of favor. But then somehow it came back into favor around about 1989. Okay, so let's okay, let's do the deep Q learning, and then after we'll take a break, and then we'll look at some enhancements. So there's a few just different variations on the same ideas here. So we start with just the deep Q learning. Okay, so these guys, these people who went, to London to work for DeepMind, and some of them were from, I think, so there was groups in Alberta and Montreal and Toronto working on this as well. They had the idea of using these Atari games as test beds for some of these algorithms. And this is, so we already saw the video of the Pong network and the Pac-Man. So as I said, it's a convolutional network, so this is a bit more details. It's sort of a bit similar to the net. Right, so you have a stack of, you were mentioning having 2 consecutive frames. For some of these domains, they actually have 4 previous frames. They have a sequence of 4 frames. So that's the input. These are treated as different channels, the same way we had, 3 channels for a color image and so on. There's 4 channels here. By the way, Atari of course, the Atari games are originally in color, but they somehow converted to a black and white. They converted to a grayscale image. I think they just extract out the Y component and throw away the U and V. So they've got 4 black and white images here. You got 16 8x8 convolutional filters. Then you've got 32 4x4 filters. So in this architecture, there's no pooling. It's just fully convolutional, but there is downsampling. So we go from the original image is 84 by 84. That's actually downsampled as well. I think the Atari is something like 180 by 180 or something, but they shrink it to 84 by 84 and make it grayscale. And these images get so they use. It doesn't say here, but I think there's a stride of 2, which shrinks the image by a factor of 2, and then the same thing here. So these images get smaller. Then we have the fully connected layers, and then the output. So this part of the story is very familiar to us. This is what we saw with the image classification. But what about the output? How many possible actions are there? So with Pong, as we said, with Pong there's only really 2 actions. But for these other Atari games, there's more actions. How many actions are there? Well, typically, you've got a joystick and a button. The joystick can be in 9 different positions. It's like northeast, northwest, north, northeast, northwest, east, west, southeast, southwest, south, and centered, right? So 9 different positions for the joystick. And the button can either be pressed or not pressed. So when you add that all together, that's 18 actions, and they treat this as 18 separate actions. They don't treat the button as as an independent action. They just treat all these 18 as being independent. Okay. And so what they did for this original work in 2015 is they just applied Q-learning directly in this situation. Right? So the there's a lookup table. So what's going on here? There's 18 outputs. So here, the output is, so this is not softmax. The output here, the input is the state, and then the output for action A is meant to estimate Q of S, comma A. So whichever action is chosen, the output is meant to be the Q value, right? So they implement this Q learning. Okay, so, and then there's going to be some enhancements, right? But maybe I'll leave that till after the break. Okay, so, but you can see how Q-learning can be applied here. You put in a state, you get out an output for each of these 18 actions. We choose the action probabilistically. We choose the action based on the e to the power of that output is the probability of taking that action. But once we've chosen that action, then for the training, we try to train that output to be an estimate of the Q value. And we apply Q learning, right? So let's just, is there some? So I think that's what was applied here with this Pac-Man. All right, why don't we just, is there any questions about this? Okay, so let's take a 10-minute break now, and then we'll come back and talk about the further enhancements to this.
Excuse me, I just
Yeah.
want to ask questions about this one.
Yes.
This one is this
Yeah. That's right, the value of the next position.
But how can I get to the value of the next?
Well, you just wait until the next move has been played,
Oh, really?
and then you use your network to get your estimate of the value of the next position. So it's like you're using your estimate of the value of the next position to train your estimate of the value of the current.
So you will use the previous one
Yeah.
to.
You always train the previous move
Yeah.
towards the
Oh,
next.
yes.
Yeah. So this is why it's.
Can you give me an explanation like step by step?
Okay, so what I mean, in a way, what I've described so far is kind of the beautiful, elegant theory. And what I'm going to tell you about in the next few slides, in a way, is just the kind of tricks and hacks and little tweaks that people experimented with that turned out to improve the performance for certain types of environment. Yeah, so it's a little bit more sort of, this stuff is a little bit more sort of wild and woolly, but it is kind of interesting to see what works better than what, you know. So the first thing they noticed is that there's temporal. First of all, this thing here. So this Q learning, we have Q of S, T, and AT, and then our new estimate is this. And what this says is we want to update, we want to change the weights in such a way as to move our previous estimate closer to our new estimate. So that's really the same as trying to minimize this. It's often convenient to express this as trying to minimize an error term, and this is actually the same as trying to minimize this error term. Because when we remember, we're treating the Q value at the next state as being fixed, and we're only updating this. And when we differentiate with respect to this, you know, the derivative of x squared is x, or 2x, and so when we take the derivative of this, it's exactly the same as doing this. So this is exactly the same as Q learning, but it's just phrasing it in a way that we're more familiar with, that looks a bit more like supervised learning. And if we make it look like supervised learning, we can actually kind of play a game and put all this information into a table, and then we can treat it as a supervised learning test. So that's the first kind of observation that they made, is that you could split this up in a way into two threads running in parallel. One thread, the agent is playing the game, and you're collecting this database of states and actions and Q values. So the database has the database says that in this state, the player took this action and got this, calculated this Q function. So you can have one thread that's playing the game and producing all of this information, and then you can have another thread that's taking that information and treating it as a supervised learning task and just training based on that information, and then the weights are being fed back into the other network, right? So you can parallelize the task, and if you've got a lot of processors, you could have multiple, you could have several processors, and each processor is playing games, and they're all creating information for this database, and then the learning is happening. So you could have 15 processors that are all playing games independently with the same weights, and you could have one process that's collecting all this information and doing supervised learning to update the weights, right? That's the first thing. Okay, so it's parallelization. But then they noticed, well, there's also a bit of a problem here, because if let's say you play a game and you generate this series of states, they actually could be quite similar. You know, like if the states in, you see one state, and then you see another state from the same game, so it's going to look quite similar to the previous one. So you see a lot of states in a row that are similar to each other, and then when you move on to the next game, you're going to see another sequence of states that are all similar to each other, and this can kind of skew the learning a bit. So they decided, well, what we want to do is kind of mix it up a bit. So because we've parallelized this, and this is why it's called experience. This is called experienced replay. So you've got one or more processors that are playing games and contributing to this database, but the network that's learning from those examples in the database isn't just learning all the examples from one game and then learning all the examples from the next game. It's randomly picking from different games, and that actually sort of improves the learning. So if you think about this, I mean, you could think about this in relation to ImageNet. If you have 1,000 images of birds and 1,000 images of trucks and so on, it's not a good idea to train on all the birds first and then train on all the trucks and then train on all the ships. It's much better to kind of randomize them so that they're interleaved. And this achieves the same thing in this context. So this is called asynchronous, this is called experience replay, but it has this concept of asynchronicity built in there. So that's the first enhancement. And then okay, prioritized replay. Okay, we'll get to the other enhancements in a minute. This is a table of the various Atari games they trained on and how well they did. So some games like Pong and so on, they did very well. Some not so well. Maybe it's worth... okay, we'll look at some more videos in a minute. I'll tell you a little bit more about these enhancements. Okay. Yeah, so they came up with these enhancements fall into mainly three categories. So one is the prioritized replay. So they... so they have this database and then they're pulling examples out of this database, but instead of pulling them out randomly, they try to give favor to examples that are surprising, examples where the Q value is very different from what was predicted, and they give more emphasis to that. The second enhancement is the double Q learning. And the third is the advantage function. Okay, so we'll go through these one by one. Okay, so prioritized replay. This is the error between, if we think about this again as supervised learning, this is the error between, this is the QW of ST80 is the Q function that we're predicting at the current time step. The rest of that expression is the Q value that we're at the next time step. So the ones where that is the examples where that is large, we weight more heavily. So I guess if you think about this in terms of Pac-Man, maybe this is sort of like when you eat a ghost, you suddenly get a big reward. And it kind of prioritizes that, okay, something happened that I wasn't expecting. I'm going to train more heavily on that. So they just the way they pull these things out of the database, they give a bit more emphasis to those examples. Okay, now double Q learning. Now this is a bit subtle, I guess. But the idea here is that if you look at this Q learning, the Q function is being used for two purposes here. The Q function is being used to estimate the Q value, but it's also being used to select action. So when it appears here, it's being used to decide which action to take, but it's also being used as a value function. So it somehow causes problems with the learning, the fact that this Q function is being used for two different purposes. So these guys, Mani and so on, tried Silver tried a few different variations of this. So one thing they tried is they said, okay, well, we'll take two different networks. Both of them are trying to learn the Q values, but we'll split up the roles. So we'll use one network to choose the actions, and we'll use another network to train. And sometimes they have two processes going at once. So in one process, this network is being used to choose the actions, and that network's being trained. And at the same time, you have another process running where this network's being used to choose the actions, and that network's being trained. So it sounds like madness in a way, but because two things are being trained for the same purpose, but somehow it gives a better result because it separates out these two roles of the Q network. Well, then they found that they didn't really need to have two separate networks, but instead one network might be just the weights that I had a short time period ago. So I might use, I'm training based on the current weights, but I'm selecting my actions based on what the weights were 2 minutes ago or some fixed time period ago. And again, these are all kind of tricks. It's really, there's not quite clear why this gives an improvement, but somehow the older version of W using the older version of W makes the thing more stable. That somehow just the fact that you're not using exactly the same network to do the action selection, it's related to the idea of confirmation bias. You select an action and you get a high reward, and you assume that the action led to the high reward, but it may be that if you had chosen a different action, you would get just as good a reward. So it's kind of like these psychology experiments with superstition and so on. If you see a tiger in the forest and you happen to be holding a stick in your hand and the tiger runs away, you may think that the stick had a magical power to make the tiger run away, but maybe it's just a coincidence. So this is called like confirmation bias, that your learning tends to be biased according to the actions that you chose, and so just by separating these things out a little bit kind of helps to remove that bias. And then again, these people at DeepMind had a lot of computers and they could do things really in parallel, and so that fed into this as well. So they would say, okay, we have multiple processors, and each processor has its own current version of W that it's training, but in terms of action selection, they're all going to use the same W bar for action selection. So you sort of, they train for a while, and then all the weights are collected and averaged, and that gives you a new W bar, and then the new W bar is broadcast to all the processors, and then they all continue to train independently, but all using the same action selection network. Yeah. So it's sort of, there's this, a lot of these things are sort of intertwined, the parallelism and the double Q learning. And then the third enhancement we have is the advantage function. So this goes back, if you remember back to the reinforce algorithm, we had this baseline. So we found that if we subtracted a baseline from the reward to make some of them positive and some negative, the learning becomes faster, more efficient. So this is the same idea being applied to this Q learning. So we say, if you think about it, remember we got this value function, we got this Q function. So the value function is the rewards that you're going to get if you start from state S and do the sorry, how should we put this? The Q function, you have to do action A first, and then you can follow the policy. The value function, you're allowed to choose whatever action is favored by the policy. So if we subtract the value function from the Q function, this is saying how much extra benefit am I going to get by doing this action compared to the action I would otherwise have chosen. Yeah. Often it's negative. It could be how much worse is it going to be if I choose this action instead of the other action. And so this can act like a baseline, and then right, so when we take the argmax of Q, that's the same as taking the argmax of this advantage function because the value function only depends on S. Right? So, sorry, I think that's a slide that's, I think these slides might be repeated from the previous hour. But finally, we get to this advantage actor critic. So, so this is the sort of this was the next generation after the deep Q learning was called A3C. It was the asynchronous advantage actor critic algorithm. So asynchronous because of the reasons we described with this action replay. It's an actor critic algorithm, and it uses this advantage function. Yeah. So it's the same as this, but instead of having R total minus B, we have Q minus V. Okay, so this is how it works. And again, this is really just, they tried a lot of different combinations. And it turned out that this particular combination works well. So they have a policy network. So remember, with double Q learning, we had the actions being chosen either by the same Q network or a different Q network. Now we've separated out the policy network and the Q network. So we use the policy network to choose our actions. We need to keep an estimate of the value function, so we use TD learning to update our estimate of the value function. And then we do Q learning, but the way we do Q learning, remember Q learning is meant to estimate the weighted sum. Q learning is meant to represent the weighted the cumulative reward several time steps in the future, but weighted by this discount factor gamma. So they take advantage of this. They estimate this more directly. They say, well, I've got an entire sequence here, so I'm going to actually look at the rewards. I'm not just going to look at the next reward and the Q function at the next time step. I'm going to look at the rewards that I get for the next n time steps and calculate this weighted sum, and I'm going to use that to update my Q function. And then when I get n steps in the future, that value function is meant to estimate what will happen after the nth step. All right, so this is just gives a bit more accuracy in estimating the Q function. And then the policy is updated by this policy gradient, but we're subtracting off the value function, treating it as a baseline. And the way we learn the value function is as a weighted average of the Q functions. Right, so all these pieces come together. We're simultaneously learning the value function, the advantage function, and the policy. Yeah. And by using this method, they were able, on many of those Atari games, this was able to learn better than just the deep Q learning. Okay. Any questions about this? Okay, well, I wanted to come back to this hill climbing because there's been quite a bit of recent interest in this as well. So this is just a reminder of the algorithm we used for the simulated hockey, for example. Now, there was a paper. There's been a few papers recently. So there's a big paper by OpenAI last year, and then some follow-up papers by some other groups, where they try to use versions of this, version of this evolutionary strategy to try to do some of these domains like Pong and so on, and some other domains that I'll show you in a minute. Now it's kind of similar to the old algorithm, but all right. So how does this work? So the champ, instead of calling it a champ, we call it mu. So we imagine that we've got a Gaussian distribution, and mu is the center of that distribution. So mu is playing the role that was previously played by that champ, and then when we create a mutant, we generate random samples from a standard Gaussian distribution that we call E. So we generate samples that we call eta I that have a mean 0 and a standard deviation of 1. And then the mutant, for each coordinate, we take the value of the champion and add this random number times that sigma. And so often these sigmas are fixed, but sometimes they may vary. And the other difference is to do with this, how far we move. So in the earlier algorithm, if the mutant was not as good as the champ, we didn't do anything. And if the mutant beat the champ, then we moved a fixed amount towards the mutant. So these guys actually scale the movement according to the difference in the fitness. So if the fitness of the mutant is much bigger than the champ, then they move a big distance. And if the mutant is worse than the champ, they actually move backwards away from the mutant. Yeah, so they scale this according to the fitness. So the way it works is you kind of keep a running average of the fitness. Again, this idea of the baseline. And then so you look at the fitness of this, and then you're not comparing to the champ, but you're just comparing to the average fitness over several mutants. So you look at the fitness of this particular sample compared to the average fitness, and if this sample has a bigger fitness than the average, you move towards it, and if it's got a smaller fitness than the average, you move away from it. So this gives a sort of evolutionary algorithm. Now, let's just have a look at some of this in practice. All right. Well, it's interesting to have a look at some of these Majoku and OpenAI gym environments. So this one here is a very old environment called the lunar lander. And this is so old, these sort of programmable calculators that came out in the 1970s included this game. Like you'd be told, the idea is you have to land, you have to adjust the thrusters of your lunar lander so that you land gently on the ground. And in this game, you'd be told your elevation and your speed, and you had to type in a number that was your thrust, and then it would tell whether you'd landed safely or not. So this is one of the environments here, and we can apply these sort of learning algorithms to this. I think this is Q, yeah, this is Q learning that's being applied here. So eventually it kind of manages to land smoothly on the ground. Okay, what else can we have a look at here? Oh yeah, the inverted double pendulum. So there's a version of this with there's a version of this with a single pendulum, but that's fairly easy. But this is a bit of a harder version where you have kind of like an articulated pendulum, and you have to try to balance both of them. And again, I'm not sure exactly which algorithm here, but it's probably Q learning. And eventually, after quite a bit of training, it manages to balance. See, it's a much harder task than the single one, but it does manage to do it eventually. Oh, there it is. And for the third assignment, you might be applying Q learning to a couple of these kind of tasks. Okay, so that's the double pendulum. There's, well, the other task that's interesting is the mountain car. So the reason this is interesting is because you need a lot of exploration to learn this task successfully. So the way this works is you have to apply force on this little wagon thing, and you have to get up to that flag. And the only way to do it is to kind of go back and forth a couple of times and build up your potential energy to eventually get fast enough to go up that hump. And this video is kind of gives you some idea of how long the thing really takes to learn. Yeah, I think Oscar Wilde said that the game of cricket was invented to teach English schoolboys the meaning of the word eternity. And this is, if you actually watch the full 16 minutes of this, you get very, very bored. But it really shows you how long it actually takes to learn this kind of task. But it's an interesting exercise to try to write one algorithm that can learn all three of these tasks, because they kind of, this one really relies heavily on exploration, whereas the others rely on sort of other factors. Yeah, it does get there in the end, I think. I'm not sure whether you have to stop on the flag or just go through the flag, but eventually it does get there. Yeah, it has to go all the way up here and then kind of take a running jump. And I couldn't find any video of this, but I know some people have experimented with environments where you have an inverted pendulum. You have a pole on top of the cart, and you have to simultaneously keep the pole balanced and get up to the flag. Now this one is interesting because this is the same double pendulum task, but they're applying this kind of evolutionary algorithm or some kind of genetic algorithm. And I really like this visual because I think the way it's working is like there's a population here, and the ones that fall off the edge die, and the ones that are surviving breed to replace them. I think that's the way it works. And yeah, again, eventually it does learn to balance the double pole. Mountain car. Now, there's a couple of others that involve walking, bipedal walking. If you have a look at OpenAI Gym, you'll see all of these environments. So this is a kind of simple, simplistic sort of two-dimensional bipedal walker, and this is learning by one of these evolutionary strategies. So you see it's sort of making some progress there, and then after a while it looks a bit sort of funny, but does actually manage to make progress. And there's a lot of sort of subtleties about this. The way the OpenAI Gym thing is set up, the penalty, sorry, I'm just trying to freeze this to show you. So the penalty, the way they have this set up, you get a reward for how far you move forward, but then if you fall over, you get a big penalty sort of thing. Or but people have pointed out that the task is actually much easier. The task is actually easier to learn if you just have the pure reward of how far you move forward and take away the penalty for falling over. Putting in the penalty for falling over actually makes the task harder to learn because there's this kind of local optimum where the thing just sort of stands there with its feet apart and doesn't move, because that way it doesn't move forward, but it avoids the penalty for falling over. So this is kind of similar to what happened with the simulated hockey when we added in those extra reward terms that led to funny behavior. The same thing can kind of happen here. But some people are interested in that. Some people are interested in the idea of, well, if you have a fitness function that does have a local optimum, can you have an algorithm that will escape from that local optimum? But sometimes they introduce the local optimum in a quite unnatural way. I think this is the same thing, but having it go over a slightly more uneven terrain. It's kind of impressive that it gets over that square obstacle in particular. Yeah. Now this is another walking environment that's like a three-dimensional walker. This is sort of a humanoid walker, and I think that this is PPO, but no matter whether you can do this either by evolution or by reinforcement, other types of reinforcement learning, but it often learns these very strange looking zombie gaits that do move forward but look quite unnatural to us. Yeah. Okay, what haven't we not? Breakout. Yeah, this is interesting. Sorry. So let's have a look at some environments where things don't work very well. So breakout is an example where so far evolution hasn't worked very well on breakout. It learns Pong. It learns Pong pretty well, but it has trouble with breakout. But DeepMind's Q-learning managed to learn breakout quite well. So the way this is this game that was famously invented by Steve Wozniak before he started Apple. You knock out these bricks, and this is the early stage of the learning. It's not doing too well. This is after, 2 hours of training. I'm not sure what kind of processor or how many processors it was using, but 2 hours of training. It's doing a pretty reasonable job. It's knocking out the bricks. So it's sort of similar to Pong in a way, but I think this gets to the heart of what the previous guy was saying. The difference between this and Pong, in Pong, if you look at 2 frames, the things that are different between the 2 frames gives you all the important information, really. But here, that's not the case. Here, things that are sort of stable for quite a long time are still very important. And so eventually after, I think, sorry, I think I missed that, but eventually after 48 hours of 4 hours of training, it eventually learns this this very nice strategy where it preferentially knocks out bricks on one edge to create a hole, and then it sends the ball up through there so that it bounces around on the back. Yeah, so it's quite impressive that it learns this strategy. Sorry, just a couple more videos because these do illustrate different points. Pong. Now, there's something a bit funny about this version of Pong, to be honest. Well, it is taken from. So normally Pong is. Someone was asking about this in the break. Pong is normally a 2-player game, and we really would like to be able to control both players and do a sort of co-evolution because we think that would give a better result. But it is a 2-player game, but the people who've built this environment have so far only implemented the 1-player version where you're playing against a fixed opponent. And it's quite a bit of work to interface this. You have to be able to extract the screenshots out of the interface with this machine code from this 1980s architecture. Now let's have another look at this same Pong video we looked at before. I think it's this one. Tell me if you see something a bit unusual about this environment. So this agent, in the beginning it's kind of getting thrashed. Now, by this stage, it's getting a pretty high score, but do you notice something a bit unusual about the green player's strategy? Have a look at where the green player is when it hits the ball. Do you sort of notice that the green player's in roughly the same position whenever it hits the ball? Yeah, so I think this particular framework, it's sort of forced to jiggle about a bit, but with the evolution, it's not required to jiggle about. It's allowed to stay in one place. And so this, if you look here, this player has actually learned a good strategy, but a very simple strategy. It gets to this particular place and then it never moves. So I think there's something a bit kooky about some of these environments. I think it's often the evolution does solve Pong, but it might be doing it by just finding this really crazy. So I think there's just something a bit funny about the way this environment is set up. I don't know. Yeah, you can win 21-0 without actually moving. Okay. And finally, All right, well, okay, that's probably enough. I'll come back. There's a couple more videos I'll show you at the end. Now, I just wanted to say a little bit more about this evolutionary strategies. This is a little bit involved, but part of the reason I'm telling you this is because we have to introduce this. We have to introduce the concept of KL divergence because we're going to need it later in the course. Okay, so these OpenAI guys found that this evolutionary strategy was competitive with Q-learning on some of these tasks. Now, but then you can ask, well, maybe I want to update sigma, so in the base algorithm, I'm making the same size changes to all of the weights, but maybe the outcome is actually more sensitive to some weights than others. Maybe I should be adjusting these sigmas so that I make bigger changes to some weights and smaller changes to others. Now, there are a couple of ways to try to do this. So there's more sophisticated kinds of evolutionary strategy. There's where you sample, you take a number of samples and then you look at the top 20% of samples and you make some adjustment based on this. I won't go into the details of those. There are other methods where we try to backpropagate. We try to learn the optimal value of sigma as well as mu by backpropagation, or sometimes minimizing the reverse KL divergence, and this is known as variational inference. So again, this is getting a little bit beyond the really the scope of the course, but I can see there's a few sort of equations here, but basically the way it works is this. We have a certain, what we're really doing is sampling from a Gaussian distribution, right? We have the center is mu, and then we're sampling from a Gaussian distribution in each direction. And so we use Q of theta to represent this Gaussian distribution. And what we want to do is we want to adjust the distribution so that the fitness, the average value of the fitness in that distribution is high. And we can create a Boltzmann distribution based on that fitness. So this is the same idea as softmax, except we're doing it over a continuous set of variables, right? So we want the fitness of, we want the probability to be proportional to e to the power of the fitness of, we want the probability of theta to be proportional to e to the power of the fitness of theta. And so what we might want to do is try to minimize the distance somehow between this q theta and pt of theta. So we've only got we're forced to have a Gaussian distribution with these parameters, but what we can try to do is estimate the distance between this distribution and this distribution. And if we calculate this KL divergence, it actually looks quite similar to the equation that we had before, because this is the fitness of theta, but then there's a term here which actually, the T log z is the normalizing constant, so we can kind of ignore z when we do our backpropagation. And this T log q of theta, this is actually a term which tries to keep the distribution spread out and prevent it from kind of collapsing down to zero in a particular direction. So this is a kind of regularizing term which forces sigma to be away from 0. Now, okay, so, and this comes from minimizing the KL divergence. Okay, so what is the KL divergence? Well, I've got two distributions, and I want to measure the distance between those distributions. So look at the top example and the bottom example. You know, if you look at the green distribution and the blue distribution, are they similar? Are they different? Or if you look at the blue distribution, let's say the true distribution is the blue one, but I need to find but that's not Gaussian. A Gaussian distribution has a single peak. This blue thing has two peaks. So what I want to do is I want to find a distribution with one peak that somehow approximates the blue distribution. So which is a better choice? You know, this choice is good in a way because it approximates one of those peaks, but ignores the other peak, and then this sort of makes a compromise between the two peaks. Yeah, so what this KL divergence does is it kind of measures the distance between two probability distributions, but it's not the same as a distance because it's not symmetric. The reason it's called a divergence is because it's not symmetric. The divergence from Q to P is not the same as the divergence from P to Q. Okay. Now, the way this is defined is as follows. It's the integral over theta of Q of theta times log Q of theta minus log P of theta d theta. What does this actually mean? Well, there's this thing called the entropy of a distribution. So the entropy of a distribution is the integral of Q theta times log of Q theta. And in information theory, this is the amount of information required to transmit a random sample from Q. Now, there's this whole, you can define it for discrete distributions, and then this is for continuous distributions. So when we say transmit a random sample, you have to specify how many digits of precision you're going to send and that sort of thing. But in the case of a Gaussian distribution, the entropy is just the log of the standard deviation, log of the sum of the log of the standard deviation in each direction. So what this is saying is that if we want to increase the entropy, the wider the standard deviation, the bigger the entropy. And if the standard deviation starts to get close to 0, then the entropy becomes very small, and a very heavy penalty is imposed for that. So this is a bit like the weight decay that we had to try to prevent the weights from getting too big, except here it's actually preventing the standard deviation from getting too small. And if you're interested, there is an information theory interpretation of this KL divergence. This is saying that it's, well, if you devise a code which is optimal for the distribution P, but then you're forced to draw samples from Q and transmit them using a code designed for P, and how many extra bits do you have to send in order, because the code is designed for P instead of Q? I don't know. So if you know information theory, maybe that'll make sense to you. But it's probably better to just look at these images. So if we we can choose to maximize, we can choose to minimize either the forward KL divergence or the backward KL divergence. So we can either choose to maximize the KL divergence from Q to P or from P to Q. Now, if we maximize the forward KL divergence, we tend to get this answer here that gives an average between the two peaks. So when we do, in some situations, like when we do robot navigation, or object tracking, we always maximize the forward KL. We always minimize the forward KL divergence, because if there's an incoming missile and it could be here and it could be here, and we think that it's here, that's a total disaster, because if it ends up being out here, then we're not going to respond to it and we're going to get hit, right? So this is a much better solution because, okay, the missile could be here and could be here, but I'm choosing a distribution that's wide enough that it covers both possibilities, right? And it doesn't have to be a missile, but I'm just sort of looking for, or it could be something that I'm trying to hit. I want to fire a missile at somebody else's ship. If I'm very confident that the ship is here, but it actually turns out to be here, then I'm not going to hit it, right? But if I'm using this distribution, then I'm covering both possibilities, right? So in most sort of traditional situations, it's the forward KL divergence that we want to optimize. But in these neural network situations, we actually optimize the reverse KL divergence, because in these situations, we just want to find a policy which gives us a high fitness. And so what the blue thing is saying is, okay, if we follow this policy, we'll get a high fitness, and if we follow this policy, we'll also get a high fitness. We've converged on this policy, but it really doesn't matter, because at least we're getting a high fitness. Maybe there exists some other way that we could get a high score, but we found one way to get an equally high score, so that's perfectly fine. Whereas if we were going to do this, we're sort of being non-committal. There's two good policies, and we're kind of trying to do something in between and maybe not getting a good fitness. Yeah. Okay, so I hope that even though these equations are a bit scary, I hope that this explanation makes some logic. Okay, and then, all right, so why am I mentioning this KL divergence? Well, there are some other reinforcement learning algorithms that directly make use of this KL divergence. We're not going to cover them in this course, but you might be interested in them. So one of them is called Trust Region Policy Optimization, or TRPO. But the other thing is this KL, after the break, we're going to be talking about variational autoencoders for images, image generation, and this KL divergence is going to come back in that context. Okay, any questions about that? Yeah.
So for that evolution strategy here,
yeah.
why we cannot use a priority queue to store the best 20% fitness samples? Like you the tree you told us before, use a priority queue.
So for the evolutionists, you could do that. Yeah. You could store the best samples in a priority queue, and then what? Use them to update the policy. Yeah, there are ways you could do that. Yeah. Good. Okay, I think we'll just show a couple more videos. There's just a couple more videos here. There's just one more video. This is showing So this is an example of an environment that actually these methods don't work very well on. This is a game called Montezuma's Revenge. This is a video of, I think, a human playing it. So you see the guy got the key, and then he's going up this ladder, and he goes into the next room. And I mean, there's a few interesting things here. You can see why you might need a longer time frame than just, 1 or 2 frames ago, because these force fields, if you get caught in these force fields, you're going to die. So you have to your strategy has to adapt to sort of avoid these force fields, even though they're not there all the time. But the more interesting thing is the following. Well, you notice how you move from room to room. And you've got the key. This thing up here tells you that you have the key. And then eventually you're going to get to a room where there's a door, and you're going to need the key that you got at the beginning of the game to open that door. So let's sort of think this through. So this is sort of the next stage that people are sort of thinking to. All the methods that I've described are kind of monolithic in a way. You have one neural network, and it's trying to learn the whole task. But here, when you move from one room to another, the images look very different from the first room to the second room to the third room. So you can sort of start to think to yourself, imaginatively, if you wanted to come up with new algorithms, it might be better to have different networks that are, each network is tailored to one particular room somehow. But you would want the algorithm to figure that out for itself rather than being told what room you're in. And then the other issue is this thing about the delayed reward, that somehow we need to pick up the key, and then we need to use the key 2 rooms later. So it could be that we use, humans probably use, oops, he died. Humans use kind of domain knowledge in a way to learn these tasks. I mean, we see a key and we're familiar with the idea of a key, so we think, oh yes, I'll get that key, and then we know that we're going to likely use it to open a door. But the AI doesn't have that background knowledge. Somehow it has to randomly pick up the key and then open the door later. So maybe you would need some way to combine symbolic methods with neural networks. Yeah. So you can see these are sort of remaining challenges. Okay, so these are just sort of a list of kind of current issues. Yeah. Augment A3C with unsupervised auxiliary tasks, encourage exploration, increased entropy. So there are some algorithms that actually don't make use of the reward, but just try to get you to explore new places. If you see something new that you haven't seen before, you treat that as the same as a reward, right? So if you think back to the Montezuma's Revenge, I don't have a video of it, but if you look at how these deep Q networks actually play, they get a very low score. Often they never move to the second room. Often they stay only in the first room. So if you give a reward for seeing something novel, then it may encourage it to move into the second room, even if it hasn't gotten a reward. There are other methods that are trying to take actions for which rewards are less predictable, or concentrate on features of the environment. which make the action more predictable. So, this is sort of to try to filter out irrelevant information. Maybe there's an environment where there's trees blowing in the wind or a river flowing through the environment. There's a lot of kind of information in there, but it may actually be irrelevant. From a point of view of information theory, the trees provide a lot of information, but it may be irrelevant information. So you're trying to concentrate on what's relevant. People are also looking at transfer learning between tasks. I didn't mention supervised learning. So there's supervised learning where a human plays the task and then the agent tries to learn from what the human did. And there's recently been a lot of interest in inverse reinforcement learning. So you're given a policy, and then you have to predict, you have to guess what the rewards are from. You look at the way the human played the game, and then you have to guess what the rewards are based on watching what the human does. And there's also other combinations. So these are the things that people are exploring, basically. And here's some references. Okay. Any questions about this? So let me just see whether this. Let me see whether I can get the document camera to work. It didn't work last week. Okay, we got it on one screen. Okay, we've got it on two screens. I know it's been a long day, but I might just, in the few minutes we got left, I might just say a little bit about this exercise on reinforcement learning. Just to have a bit of a discussion about this. So this is, if you click on the website, there's a list of quizzes and a list of exercises. So let's just have a quick look at this. So you're given a set of, we imagine an environment with two states and two actions, and we're told what the rewards are and what the transitions are for each state and action pair, and we can draw it as in a diagram like this. And then we're asked, what's the optimal policy? So let's just, and then further down you're asked to compare every possible policy. So let's just have a bit of a discussion about this. So let's say that the discount factor is gamma. How would we be able to compare? Let's say we start in state S1, and I'm thinking about taking this action twice and just I'm thinking about just taking this action over and over, or I could take this action and then this action and alternate. Now, how would I decide which of those two policies is better? Sorry? The reward, right? Now, in this case, sometimes I have to look at the actual infinite reward, but in this case, it's probably okay to just look at the next two time steps, because if I do this twice, I come back to S1, and if I do this and then this, I come back to S1, and I keep doing that. So if I do this twice, and if the discount factor is gamma and I do this twice, what reward am I going to get? The first time step I get 1, and the second time step, right, I get gamma. So in one case I get 1 plus gamma. Now what happens if I do this and then this? What rewards do I get in those two time steps? Minus 2 plus 7 gamma. Now, for what value of gamma are these two equal? Well, 3 would equal 6 gamma if I collect things up. So gamma is equal to 1/2. So, all right, let's think about this a bit more. Let's suppose gamma equals 0. Let's say I'm in state S1 and gamma equals 0. If gamma equals 0, that means I only care about the first time step. I don't care what happens afterwards. So which action would be best in that situation? A1, right? So if you look at this, basically if gamma is less than or equal to 1/2, it's better to do this. If gamma is bigger than or equal to 1/2, it's better to do this. So you can get an idea of this. Now, if we want to, let's say we want to think about doing this and then this, that's a bit more complicated, right? So we probably need to think about it in terms of infinite reward. So if I do this forever, if I get 1 plus gamma squared plus gamma cubed. Now, what did we say that was equal to? 1 over 1 minus gamma. Now, what happens if I do this and then do this repeatedly? So the first time step I get minus 2, but then after that I get 3 gamma over 1 minus gamma. That's right. So then if I multiply by 1 minus gamma, I get 1 equals minus 2 times 1 minus gamma plus 3 gamma, which is minus 2 plus 5 gamma. So gamma is equal to 3/5, is that right? Well, now let's think about starting from S2. If you're starting from S2, would it be better to do what? If I start from S2 and I do this twice, what am I going to get? I'm going to get 3 plus gamma. If I do this and then this, what rewards will I get? 7 minus 2 gamma. 3 plus 3 gamma, thank you. So then what's this? 5 gamma is equal to 4. So gamma equals 0.8. So if gamma is... so if gamma was 0, which option is better? The plus 7. So this is better if gamma is less than 4/5, and this is better if gamma is bigger than 4/5. So you can use this to kind of figure out what the optimal policy is. Okay, the details are all down there. All right, now the other thing I just wanted to talk a bit about the Q learning. So when gamma is 0.7, it's in between these two values, actually. So it turns out the optimal policy here is this one, where you go the minus 2 and then the plus 7. There is a fourth policy. The fourth policy would be from here you do this and from here you do this. It turns out in this case that policy is never optimal. Okay, so the optimal policy is pi star of S1 is A2 and pi star of S2 is A1. Now how do we calculate the value function? Well, one way to do it is by simultaneous equations. So if I start in S1, I do minus 2 plus gamma times V of S2, and if I start in S2, I get 7 plus gamma VS1, and then I can solve these simultaneously. Yeah. So I think you can work through that, and these turn out to be the actual Q values. Yeah, So you can see the optimal policy is got by taking the maximum number in each row. So from S1, it's better to take S2. From S2, it's a little bit better to take A1. Now, I just wanted to go through a couple of steps of the Q learning so that you can see how this works. So let's draw a table here. So this is S1, S2, A1 and A2. So I start off with just 0 in each place. So how does Q learning actually work? Well, in the beginning, I don't know anything, so I just have to make a random choice. Yeah, so I'm starting in S1, and I just randomly pick between A1 and A2, but let's assume I pick A1. So then I say, okay, well, I did A1, and I got a reward of +1. So I then update my estimate. I say, okay, I was in state S1 and I did A1, so I used to think this was 0, but now I'm going to say that it's 1. And then I'm back in S1 now, but now I have to choose between A1 and A2. Well, from my table, it looks as if A1 is a better choice, because I think this is worth 1 and that's worth 0. Now, if I choose A1 again, then my next estimate is I say, okay, well, I got 1 as the immediate reward, but I thought my estimate of S1 and A1 is 1, so my new estimate is 1 plus 0.7, right? So now this is 1.7. So this is why exploration is necessary, because if I always pick what I think is the best action, I'm just going to keep doing A1 forever. Eventually this will converge to the correct, eventually this will converge to 1 over 0.3, but everything else will stay 0, right? So at some point I have to force myself to do exploration and force myself to do A2. Now, as soon as I do A2, then I say, oh, okay, I was in S1 and I did A2, but I got so now I think this is -2. And then from S2, I have a choice. You know, let's say I pick A2 initially, then this would be +3. So again, we get the same problem. If I'm in S2, I could just keep picking A2 forever, but that's really not the best option. So eventually I have to force myself to pick A1. Now once I pick A1, then I realize, oh, I got a big reward, right? I got 7, and I think that S1 is worth this, so then this will become like something a bit bigger than 7, you know, maybe about 8, you know. But back in S1, I still think A1 is better, so I have to force myself to take A2, and then once I take A2, I say, okay, there's -2 here, but then I have to add gamma times 8. So this becomes like, 5 or something. And once I get to that point, then I prefer what are actually the best policies. And if I keep going, eventually I will converge to these values. Yeah. So I think this is an interesting exercise because it just kind of shows you the importance of the exploration. Good. Any questions about that? Yes. The size of the matrix. So the agent, it's a good question. So in the most general case, the agent would be told in the most general case, it could be that some actions are possible from certain states and some are not possible. But yeah, so we have a set of I mean, usually the agent is told what the set of actions are, and then it's told what state it currently is in, I guess. So yeah, in these kind of so in a small environment you can have a lookup table, but in a sort of serious environment like in Q-learning, the number of states is not really finite. So that's why we need, the number of actions is specified. Yeah, there's 18 actions and that's it. But we need actually a neural network to estimate this Q function because it's too big to just draw up a table. Yeah.